In this video, I'm going to be talking about how bases and components of vectors can actually be derivatives. And so in the first part, I'm going to talk about vectors. In the second part, I will talk about covectors. And so I have drawn right here, or written rather, the standard way that we're used to seeing vectors represented as a linear combination of the basis vectors. So the E1 and E2 being basis vectors, the V1 and V2 being the components. But we can also represent it like this, and this F should actually be an R, so I have it as R everywhere else. So it's dr d lambda, where lambda is the parameterization. And so the parameterization is usually thought of as maybe time, for instance. And so this is a linear combination of the chain rule, essentially. So we can see that there's an x in the denominator here and an x in the numerator here. But we can think of these partials of r with respect to x and with respect to y as being the basis vectors. So those can be considered like the basis vectors, and I will show in a little bit how we can think about that sort of geometrically as basis vectors. And then the dx d lambda and the dy d lambda can be thought of as components. And so I have this arrow going over here. So this is just the same thing, except I put it in this convention where we use xi, so x1 and x1, x2 and x2 rather than x and y, because that way we could more easily add higher dimensions on it. I'm going to be using 2 dimensions pretty much throughout this thing. So this image right here is actually 3 dimensions, obviously, but you could just imagine that we could add a plus, d, z, d, lambda, d, r, d, z here. And if we did it in this form, it would be dx3, d lambda, dr, dx3, and you could go on and on for as many dimensions as you want. But just for the sake of keeping it simple, I'll be mostly talking about in terms of 2 dimensions. And so this dr d lambda here is actually a tangent vector. So that would be this vector right here on our curve. So this curve is in this image, it would actually be in terms of x, y, and z, but it's the dx the dx d lambda, dy d lambda, and dz d lambda, because we are changing our x in, I guess you could think about it as time. So the x changes over time, the y changes over time, and the z changes over time, and that's how we end up getting this curve. And then this dr d lambda is the tangent to it. And you can think of a line as just being a bunch of infinitesimally small tangent vectors added together. And in fact, you will often see it as sort of an integral of the dr d lambda and then d lambda. You'll often see it written like this because it's just the sum of all these tangent vectors, infinitesimally small tangent vectors put together. And so once again, we have our dr dx here as our basis vector. We have our dx d lambda, and this one would also be true of dy d lambda, and the dr dy and so forth. But I'm just for clarity putting one each here. So the dx d lambda is the tangent vector component, and so actually on the right side over here, so I have the dr dx as our e sub x, and the dr so this should be dr dy as our y basis, and then we can actually put this in a metric tensor. So it would just be dr dx dot dr dx for the first part, dr dx dot dr dy for the second part, so on and so forth, so that we end up getting a metric tensor that looks like that. All right, and so then the dot product, so the vector length is just the drd lambda, the magnitude of drd lambda squared. And so once again, that is a linear combination here of the bases, and then the components is the dx d lambda, or dxi d lambda, and dxj d lambda. And so then we can sort of factor out the two components here, and we end up with this. And then this right here is just the metric tensor, and so we have this. And so you will often see tensors drawn or written this way, with the components out front, and then the metric tensor being the bases. So let's talk about how a derivative can actually be a vector. And so we have here, so this r here and then this r2 are both position vectors. So they're telling us the position, so from the origin. And so we're at this position here and this position here, and then this r minus r2 is the difference between those two vectors. And so that would just be the r of x plus h and y minus r of x and y. So r is a function of x and y, because we're looking at just the change in x here. So we have our x and our x plus h here. We're not changing up or down here. So this is just looking at the x, but you could do the same thing for the y as well. And so then if we take the limit as h approaches 0, so this x and this x will both cancel out. This h will approach 0, but so will this one. So the denominator and the numerator are actually sort of shrinking at the same rate. And so over here I have where we've moved the x and x plus h even closer together, but this vector here stays the same size, and it's pointing in this direction. And like I said, we could do the same thing. Sort of. In fact, I'll even put that in green here. So we could do the same thing with y. So we could have some r sort of going up here. So maybe we could call that r3, and then sort of have that shrink in towards there. And so we can see how this green one here and this green one here sort of look like bases, don't they? And so that's what our partial d are with our partial dx, which is what I said are the basis vectors. And so we can see how those become basis vectors. And so down here, I actually have it, I guess you could say, sort of zoomed out. So this curve, this in orange right here, is this sort of curving line going right there. And so that is, so I wrote vector space, but you could also think of that as the field. So that's sort of the numbers that we are interested in. So a lot of times when we think of a field, we think of, like a two-dimensional field, like we have this two-dimensional space, and a vector field, has a vector at every point in the field. But a field can be a single one-dimensional line as well, because there is a vector at every point on the field, and in fact it's the tangent vector at every point in the field that we're interested in. But we see these green lines that I had right here become our basis, and so we have this in green as the basis. But then we are also taking the dx, so the change in x as we change lambda, and then we multiply that by our change in position vector with a change in x, and we actually get we actually get the x component and the y component of a tangent vector. And I've sort of drawn this tangent vector, really large. I've exaggerated a lot. But the idea is that we get a tangent vector, and we could do that at any point on this orange line. And so just adding all those infinitesimally small tangent vectors together is what gives us the line. And so that is how we can think of the partial r, partial x as the basis vector, then this dx d lambda as a component to that vector, because we have this yellow line right here, which is sort of the x part of our tangent vector, and then we have this yellow line as the y part of our tangent vector. And so that's how we can think of derivatives as vectors, or at least the components and bases of vectors. And then obviously this right here, which is our tangent vector, is essentially what generates this entire line here in the darker orange. All right, so that's fairly straightforward. So the next part is thinking about bases and components as derivatives for covectors. And covectors, so vectors are something that I think most people, at least once you're trying to teach yourself tensors, you've probably encountered vectors before, but this idea of a covector is a little bit strange, or it's a little bit different than what you're used to with vectors. And so with covectors, what we actually have is so these blue lines are the covectors, and so they have a direction which would be represented by this arrow, for instance. And so it's kind of like a field. In fact, if you've heard of covectors, you've probably heard that covectors are often the gradient. So the gradient of some function is often thought to be the covector. It's not really. I mean, the difference is subtle, and I'm not going to really go through it here. So I know the eigenchris in his tensor calculus playlist actually goes through what the difference is between a gradient and a covector field. But like I said, this is kind of a non-rigorous intuition sort of playlist, so I'm not going to sort of differentiate between a covector field and a gradient field. And so we can kind of think about a covector field like it's a gradient field, where so everything on one of these lines is equal. So the value of our function, which would be of x and y, is equal everywhere on this blue line here. So it's equal everywhere on that blue line. And so the arrow points to the direction in which it is increasing. So our function at this line is larger than our function at this line. And so these lines here represent a sort of pretty simple function, because you can actually get lines that are, that would be curved like this, or even, like this, and stuff like that. And I'll actually talk a little bit about that here in a few minutes. But anyway, that is what a covector is. And so then when we take the dot product of a vector and the covector, which is the inner product and is actually what the dot product is. So the dot product is a vector dot a covector. And so what that is we have this vector here, which is the arrow. Then it's going through these covectors. So we see that it spans 5 lines. So 1, 2, 3, 4, 5. And so what this would mean is that our vector dot with our covector here. So with our covector, I'll put that in blue since those lines are blue. would be equal to 5. And so that is the dot product of this arrow here with this covector field. And in fact, if these lines represented something other than just 1, so say it was like 100 and 200 and 300 and 400 and 500, so it's spanning each of those lines, this would actually then become 500. And so that is how the dot product actually works, sort of geometrically thinking. And so down here we have the covector with a basis vector. And so we see that this spans 2 and a little bit here of these covector lines. So this crosses 2.3 covector lines. This one crosses 2. And so we can actually see that that if we take the x and y components here of our vector, so the x component crosses 1, 2, 3, 4 lines, and then our y component crosses only 1, so 4 plus 5, so the total vector spans 5 lines, and so that's the dot product once again would be 5 here, and so that is how a covector field actually works. All right, and so now we can think of this df. So f is our function, dx as our component. So this is the component here. And then this dx is our basis. And of course the dy is also the basis in the other direction. And so we have this function here, which is the colorful part here. And we see that it's a function of x and of y because it's in 2 dimensions. And so the slope over on this part of it is going to be represented as this partial of our function of x and y. With x, because this is our x-axis over here. Then this part over here is the slope of it is the partial of x and y with respect to y. And so that gives us the slope of our function. And so this dx tells us that we're looking at the slope of the function over this length of our graph here, and then the dy is this length over here. So the dx and dy are just small steps in one direction, and so we can see if we took this partial of f of xy with respect to x and multiplied it by dx, that will give us this vector right here. Then this df of x and y with respect to y times this dy will give us this part right here. And if we add those together, it will give us a covector here. And this is kind of a bad example because if we go from this point down to this point and then from this point up to this point, we just get 0, but the idea is that we are just adding some small section of this slope plus some small section of this slope here, and that gives us our covector. And so here, so I just wrote out some things. So we have our df, which is our covector, and our v, which is our vector. That's the same as doing the dot product of our vector with our covector, and that gives us a scalar. And so over here, actually, I have some instances of covector fields that you might run into in the real world, where we have this topographic map where each one of these lines represents a point of constant elevation. So the elevation right here is the same as the elevation right here, and the same as the elevation right here, and so around that whole thing. And so as we go from, say, here this way, so if we are moving this way, so this is right here is a vector that maybe we could say is our velocity. When we take the dot product of that vector with the covectors, with this covector field, we actually get sort of how high up we actually go. And so we can see that if the vector, if our velocity, for instance, is, this, then we will go up a higher elevation than if we, say, just went like that. So the faster our velocity, the further up we will go in, some set unit of time. And alternatively, if we have the same, if we have this same vector here in black, but say we go in a different direction, then we will cross fewer of these covector lines, and so we will not go up to as high of an elevation. And same, so if we then move over this way a little bit, we will go up even less elevation. And so what I have written here is proportional to steepness of f. So the steepness of f is essentially how close together each of these lines are. Right here is steeper, say, than right here. Because these lines are closer together. So the scalar is going to be proportional to the steepness of f in the direction of v, in the direction of our vector. So that is what I was talking about at that point right there, and the magnitude of our vector, and that's the difference between the black and the red lines there. So in other words, if you are traveling in some direction, and I actually used temperature here, and so this is actually a temperature map, which is kind of the same thing. So say you are right here, in North Dakota, and you move this way, then you are going into lower temperatures than if you went that same speed in this direction, or if you alternatively were going at a slower rate. So the idea works the same as with the topographic map. So if you were traveling in some direction, the temperature increases in that direction. So the temperature is a function of position f. The scalar will be larger if the change in temperature is steep, so large temperature gradient, or if you are moving fast, so large velocity vector. So the scalar is the rate of change of f when moving at some v here. And so we have our d f of x and y is equal to, so this dx and this dy are our basis, and then this partial of our function with respect to x and this partial of our function with respect to y are our components. So the dx and dy are the dual basis for the covector field. And then these partials here are the covector field components. And so the way that that is nice to think about this is if we look at it like this. So this is sort of like our basis in the covector field here. So each of these lines is some constant value, and this image right here I actually just sort of stole directly from the eigenchris videos. So I couldn't find any better example of this represented than this. And so we can see that going along our x-axis on this, so we can think of blue as more negative and red as more positive. And so if we wanted to look at it sort of in this way, it would be like just having a line like this, and in fact it would go down like that. So that's just y equals x. But anyway, so it goes from the most negative at the darkest blue here to the most positive at the darkest red right there. And so I put these little arrows here just to show in which direction this is increasing. And so in red here I actually have the basis vectors. So this whole thing is kind of like the basis covector, but this little red thing is the basis vector. And we can see if we take the dot product of the basis covector with the basis vector, it crosses once, and that's right there where the EY does not pierce through any of those lines, and so that actually comes out equal to 0. And then this is just the same thing for Y, and so we can see that our Y pierces once and our X does not pierce at all, and so the y with the dx right here is 0, and the dy with the ey there is 1. And so that is sort of, I mean, we've looked at like the, so that'd be like saying like our E1, and so putting the 1 in the upper part there is how the covector basis is represented. E1, that would just be equal to 1, or E1 dot E2, that would be equal to 0. And this would go down, and you can actually represent it as the Kronecker delta, so I, J. And so this is where we have equals 1 if I equals J, and equals 0 if I is not equal to J. But anyway, those are sort of taking the dot product of our covector component and our vector component. And so down here I actually have sort of written out, if we want to generate some covector field that looks like this, and I actually have sort of a color version of that down here. So you can see that the little arrows in here are the gradient vectors, and then these lines going here are the covector lines. And so you can sort of see how those are a little bit different right here. As I said before, they're not exactly the same, but in our non-rigorous way, we're just sort of pretending that those are the same. But the gradient vectors are in fact actual vectors, where the covectors are these sort of lines that look like this. But the idea is we could generate this from a linear combination of some component times our dx covector basis plus some component times our dy covector basis, and our a is actually going to be equal to the partial of our function with respect to x, and our b is going to be the partial of our function with respect to, well, this should actually be y right here, not x. So yeah, that should be y right there. And so this gives us, so when we add these together, we can actually generate a covector field like this that is some linear combination of these dx's and dy's. And so, yeah, I mean, you can even see down here on this one, if we are looking at the gradient, so we can see that that these lines stay pretty evenly spaced in the x direction, but not the y direction. That's why these gradient vectors are pointing more up than they are pointing right, and so that means that there is some greater component here for the y part of our covector. But anyway, this is pretty much it. So the main idea, I guess, here is just that we can in fact represent vectors and covectors as derivatives. And so once again, the way that we represent the vectors is like this up here. It's a little bit messy looking now, but it's this dr d lambda, where lambda is some parameterization, oftentimes thought about as time, is equal to a linear combination of the chain rule here. So this dx d lambda times partial r partial x, where you could see how this partial and this partial could sort of cancel each other out in a way, and this partial and this partial, and that's how you actually end up with the dr here and the d lambda, which is what we have right here. And that is the tangent vector, which remember is like this sort of bright yellow or bright orange looking one here. And then the covectors, so some move some direction in the x direction and multiply that by the slope of our function in that direction, plus some change in the y direction multiplied by the slope of our function in that direction. And that actually gives us our df here. And so, yeah, that is how the covectors can actually be represented as derivatives as well. I'm not going to go too much deeper into these. I just wanted to once again give sort of the intuition behind all of this. There are other resources linked in the description down below if you want to sort of dig in even deeper with some of these concepts here. But I hope this video helped you understand why you oftentimes see tensors represented using derivatives, which at first glance seems like kind of a weird thing. It doesn't seem like that should be possible, but I mean, if you think about it, these partial derivatives, which we are using for our bases, necessarily, I mean, by definition, have a direction. This is the partial in the direction of x, and this is the partial, well, x1, and this is the partial in the direction of x2, which is kind of like our y. And that is exactly what a basis vector should be, is it should be something that if you add it together, you have, a direction that way plus a direction that way. And so a partial with respect to x and a partial with respect to y satisfy that. And in fact, you will often see them written like this without anything here next to it. You'll see it just as these partial operators like this. And so that's just telling you essentially that we are looking at something in the x direction and something in the y direction. And so that is sort of how you can actually have derivatives be your basis vectors and your components. So once again, down here we can see how this component here multiplied by this partial with respect to x, which is our basis vector, gives us the x component of this tangent vector here. But anyway, I mean, there's way more I could go into on this. I could probably spend 10 videos, all just as long as this one, going into the meaning of all this. But like I said, these videos I'm making are with an eye towards intuition, so that if you do go watch some videos or read books where they just sort of introduce these ideas without really explaining them, you will hopefully understand what it is they're actually talking about. But anyway, I'm starting to ramble as usual. I hope you found this video helpful, and I will see you in the next video.